ओके पहले जो है ना मैं कुछ एक लेक्चर 17 में मैंने करेक्शन जो है ना अनाउंस की थी. I just want to tell you so that you note it here. If you remember in this example 3.1.2, there were two parts, and in both parts we had the same expression for the total friction. Of course, the normal force is different in these two parts, but the algebraic expression for the friction was the same. So we are not making any changes to this part, which is the dynamic friction or kinetic friction. Here, if you remember, we are not changing this factor, we are not changing this factor, but we are changing this factor. So if somebody can tell me कि हमने क्या changes में किया है. By now, highlight this one. ये पहले क्या था? Let me not notice. इसकी जगह हमने last time ये लिखा था mu sn. Now that is wrong, because this is the maximum value of the static friction. So static friction is not always at the maximum value. It will be equal to the applied force. Of course, because we are taking the sign here, so here it makes more sense to write the magnitude here. So if you plot friction, solid friction, against the applied force, let's say this is the applied force, so it will be, for smaller values it will be equal. Yeah, so if you increase the applied force, the friction force will also increase, and this straight line will follow till this maximum value, which is mu sn, and after that, okay, you have a constant value, which is dynamic friction, fd. So you see, you cannot say that friction force is always equal to this maximum value. So we need to make this correction. At that point, actually nobody pointed this out, so it just came to my mind today. Let's now go to the other important correction, and that is in this example which we started last time, 3.3.6. So here I carefully looked at the diagram in the book, and I found two mistakes which we did not notice last time. So these arrows, now I have fixed these arrows. Yeah, but in the book, if you look at the book, the arrows are this way. Yeah, and that is wrong, because when you apply force to the card and the wheel are different bodies. Of course, the axle is also, axle connects the cart with the wheel, and axle is considered to be part of the wheel. So when you apply this force, the first it is transmitted to the cart, to the axle. So the axle will try to push the wheel towards the left, because this force is towards the left. So that is the action, yeah, on the wheel by the cart, and the reaction of that will be opposite. Yeah, so the wheel will try to apply another a reaction that is opposite. So a consequence of this correction is the algebra also changes. Okay, so this becomes minus instead of plus, this becomes plus instead of minus. Now the final equation doesn't change, because these two forces cancel out anyway, so it doesn't matter whether you, even if you make this mistake, you will still get the correct answer at the end. But I just want you to notice that and not make any such mistake in the final exam. So let's move on to the next lecture. Okay, sorry, what was that? Okay, so maybe I also need to change this. Yeah, this should be 19. Yeah, but at least the file name is correct. So we now start with this. Okay, so here, of course, this is part 1, which was already solved. So we have two free body diagrams. Now the arrows are correct, and we can write two equations for the force balance for the cart. So I'm just writing force balance, and you know how to write this force balance for the cart. Force balance for the cart. And similarly, we can write three equations: force balance and moment balance about G for the wheel. With these five equations, you can solve this problem. Okay. So today we are going to start part 2, and unfortunately I forgot to correct this diagram, so you have to fix this one. Actually, the correct arrow is towards the right, and this is towards the left. I'll make this change later on because I have to make these changes in LaTeX. So these are the correct arrows. So let's okay. So in part 2, you are given a non-zero mass for the wheel, and of course a non-zero inertia for one wheel. Okay, this is one wheel. So because you have two wheels, so just like n is multiplied by 2, just like ft is multiplied by 2, just like mwg is multiplied by 2. So similarly, I will also be multiplied by 2. And remember that in this first part we were assuming that the wheel was massless. Okay, so the wheel mass was negligible. That's why the moment of inertia was also negligible. Now we take into account the mass of the wheel and the rotational inertia of the wheel. So okay, now let's write down that those two force equations for the cart. Okay. So the first equation is that we know x is this way and y is this way, and v is in the direction of x. And remember, because both the wheel and the cart are considered to be rigid bodies, so the same v applies to g as well. This center of mass of the wheel, actually this g is the center of mass of the whole body, because wheel is too small compared to that. So this point will also move at the same speed. So now I'm writing down the force balance for the cart first. So I can write v dot, yeah, times mass of the cart. And I know mass of the cart from the previous slide. This is along the x-axis. Along the y-axis, because there is no bouncing, yeah, no motion in the on the y-axis, so that will be 0. There is no acceleration on the y-axis. Now this acceleration and this actually change in momentum, the rate of change in momentum, will be because of the net force along the x-axis. So Rx is already there, so it will be positive. No, sorry, so because x-axis is towards the left, so this applied force F will be positive. Remember, this will be wrong in the book because of that wrong arrow. So it's F minus Rx. In the book you will see plus, but the correct sign is minus. And for the y-axis, because upward is positive, so Ry will be positive, minus mcg, weight of the cart, will be negative. So we now have two equations for the cart. Now we can write three equations for the wheel and plus axle, because they have been combined. So the first equation is along the x-axis, which previously was 0 because the mass was ignored, but now it will be v dot, because it's the same velocity. The same velocity is shared by the wheel as well. And instead of 1 times mw, we will have 2 times mw, because there are two wheels. The second one will be 0, because along the y-axis there is no motion, no acceleration. So first complete this. This 2ft is also towards the right, which is against the x-axis, and this r is in line. This r is in line with the x-axis, so, and with v, of course. So that will be rx minus twice ft, yeah, minus twice ft, because this is opposite. And this one, upward force, is twice n, minus twice mwg. This is downward force. And we need one last equation for the moment. The angular speed labeled here is omega, and remember it is counterclockwise. So that will be our positive direction, counterclockwise. Now omega dot is the angular acceleration, and this will multiply it by the inertia, moment of inertia, twice because there are two wheels. And on the right hand side, we need to write down the net moment resulting, not the net moment causing that. Okay, so if we look at, because this is about G, the moment of 2n is 0 because the line of action is crossing G. The line of action of this 2mwg is also crossing that, so it causes no moment. The line of action of Rx also crosses it. So these three forces, this one, they cause no moment. Only this will produce the non-zero moment. So 2ft is the force, and you multiply that by Rw. This Ry, remember, is a force. So the radius is Rw, radius of the wheel. Okay, I think it's given there, radius of the wheel. This is what I'm talking about. Don't confuse that with Ry. It looks like radius, but it is actually a reaction force. So we will write here Rw instead of Ry. And whether it's positive or negative, whether we write positive or negative, that will be clarified by the sense. Remember, the sense of omega is counterclockwise here. Yeah, counterclockwise. So we need to now see that the sense of this twice ft is forced towards the right. Yeah, so, and this is G, the center, so the turning effect will be counterclockwise, which is positive. Okay, so we don't need to put a minus sign here. Now you have three equations: 1, 2, 3, 4, 5. Okay, what is the goal? The goal is to write the equation of motion. Write the equation of motion. Yeah, we wish to solve for the translational acceleration. This is what we want to know. So you want to have an expression for v dot. Okay. Now that is only possible if we can write the equation of motion. Now how do we go about that? Of course, we need to look at which equations involve v dot. So this is one equation. This is one equation. Or maybe I change the color so that you see. Okay, I'll change the color. So this is one equation which involves v dot. The other equation which involves v dot is this one. So we can now look at these two equations. Can you see that if we add these two equations, the simplification is that this Rx and this Rx, one is positive, one is negative, they will cancel out. Okay, so I can simply cancel them out. I'll not do it now, but you just take a note of that. Similarly, I can, because now you will see the importance of this assumption. What was the importance of this assumption? The wheels roll without slipping. Now this assumption means that you can connect the linear velocity with the angular velocity. Yeah, this linear velocity with this angular velocity, and that will be connected through Rw, which means that I can now replace this omega by V over Rw. And because Rw is constant, so put a dot here, you will have a dot there. So I can now replace this omega dot, yeah, with V dot divided by Rw. Okay. Now, if I look at this equation now, I have another candidate equation involving V dot, and I can hope to add it just like I added those two equations. I can add this one as well. The problem here is that it was very easy to cancel out this Rx here and here. But this minus 2ft can only cancel this plus 2ft if we get rid of this Rw. So I need to get rid of this Rw. For that, I need to divide both sides by Rw. So this will become Rw squared, and on this side, this will disappear. And now I can think of cancelling this 2ft with this 2ft as I am adding these two equations. So this is now super duper because I can now add all these three equations, this one, this one, this one, plus, 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 and now I can write the final equation. The final equation will be this. Let me write this down. All these equations have V dot on the left hand side, and the right hand side, this 2ft will cancel out with this 2ft. Let me change the color. This 2ft will cancel out with this 2ft. This plus Rx will cancel out with this plus Rx. You are only left with this plus F. So that plus F will be the only force left on the right hand side. V dot is everywhere. V dot, V dot, V dot. And now in the first equation, V dot is multiplied by MC. So I'm just writing it down. In the second equation, it is multiplied by twice M wheel. And the third equation, it is multiplied by twice I divided by Rw squared. Now there you have an equation. You have an equation for V dot, and if you want, actually the actual question was to have an expression for V dot, so you can just bring this whole thing to the other side, and that will be MC plus twice MV plus twice I over R omega squared. Plug all the values and you are done. Okay. इसमें कोई question है? Do you have any question in this one? It was pretty easy. The only difference between this one and the previous one is this assumption. Because the mass was negligible here, the inertia was negligible, you had a much simpler calculation. Here, you had to be actually a bit clever to get rid of all these intermediate variables. So we need to solve the same problem now by using the energy method. This was the free body diagram method, remember? This was the free body diagram method. And the next is to write the energy method. Now for the energy method, because we know all the bodies are rigid and there is no motion upward or downward, so there is no potential energy here. Yeah, no spring, no elastic energy, only kinetic energy. So I'm just writing down the expression for kinetic energy. So the kinetic energy of the cart, and the cart is only translating. So the kinetic energy of the cart will be, I'm just writing down here, the kinetic energy for the cart, and then I'll add that the kinetic energy of the wheel plus axle. So it will be half m cart v squared. For the wheel and axle, because it is now translating as well as rotating, yeah. So because this 2ft is also non-zero and this Rx is also non-zero, so I will have to write the translational kinetic energy of the wheel plus axle, which is half mw. Mw includes that, I mean, the axle is massless, okay? So we can ignore the axle, yeah? Disregard the mass of the axle. So we are only including mass of the wheel. So half mass wheel times v squared is the same velocity, rigid body common velocity, okay? And sorry. And we also need to write a kinetic energy term for rotational kinetic energy, and that will be half. Okay, one mistake I made was this half times, this is twice mw, okay, it's not one wheel, it's two wheels. Similarly here, half I, normally I write half I omega squared, but now I have to write 2I omega squared. And omega, I know because there is no slippage, omega can be replaced with V over R W. So I can now replace this by V squared over RW squared. Now I can take V common and I can take this half common because I need to see a pattern. Half is important to be taken out and V squared is important to be taken out, okay, because it's translational motion. So now we just need to combine whatever is multiplying v squared. So it is mc, it is 2 times mw, and it is 2 times I. And don't forget this thing because we have this denominator as well. Yeah, so you have pretty much the same thing. This, you remember, is the effective mass or equivalent mass, because half, you must have mass here and then v squared. So instead of these individual masses, you now have an effective mass, which can be calculated. You can plug the values and you can have an expression for this. And once you have that, the rest is very easy. You know that writing the equation of motion is me times v dot is F, because that is the only net force. So you plug this value there, and maybe you can just divide both sides by ME, and you have an expression for V dot. So that was the energy method. Yeah. The energy method was much simpler compared to the free body diagram method. Any questions in this example? Hmm? No questions? Let's move on to the next topic. And this is important because we have so far been solving problems of planar motion only. So we will stick to planar motion, but we will have more general type of planar motion. Now, what do you mean by general? So far we did not have a general plane motion. Now, what do I mean by that? Is that the axis of rotation, this is, remember, the axis of rotation is another typo. The axis of rotation so far, this is the what we have been doing so far. Okay, so far our axis of rotation was non-accelerating. This is important. So although the axis about which you rotate, that axis can move here or there, but it must be moving with a uniform velocity. It must not accelerate, which means that neither the magnitude can change, magnitude of velocity, nor the direction. Now we will relax this assumption now. Okay, so that is what we mean by general. So we will still have planar motion, which means that we will still assume that all forces on the body and the resulting motion is confined to a plane through its mass center. So let's say you have a body with a center of mass g. So, and let's say you have this xy plane, and everything is in there, all the forces, F1, F2, anything, and all the motion, yeah, acceleration, yeah, acceleration, velocity, everything has to be in the same plane. So, and the other assumption which we have been making so far is that the body is symmetrical with respect to the plane. So ये plane इसको बिल्कुल बीच में से काट रहा है. आप assume करें कि ये अगर plane है तो इसके outside और inside, out of the page and into the page. Let's say ये page है, तो जितना outside है उतना ही in projects. This is what we mean by symmetry. Okay, so that the overall effects cancel out if you take moments about G only. So now if we go with the old assumptions, that okay. Of course, one more thing is that when we choose this reference frame XY, this reference frame is outside the body. Okay, so the calculations are made with respect to that, and that we always assume to be non-accelerating. Don't confuse this with this non-accelerating with this non-accelerating. This non-accelerating only means that we are into inertial reference frame. इस तरह न्यूटन के लॉज है ना, inertial frame of reference. This non-accelerating is you now require the axis of rotation to be non-accelerating. Okay, so this is the equation we have been using. We will no longer be able to use this equation because we will relax this assumption. So now we will take our discussion from this point onward. Yeah, not to forget that we are still in a single plane. So now if you want to write moment equations about an accelerating axis, sorry for this typo, then there are two possibilities. If that axis passes through the mass center, so if I not need to explain it here, let's say this body is rotating and you want to write the moment equation about this G, which is central. So this is the angular acceleration. So you write the angular acceleration, multiply that by the moment of inertia about g, and equate that to the net moment or the total moment about g. Now, because it is center and because we have assumed symmetry about the plane and symmetry about the center anyway, so this equation will always be valid. Now you can ask a question that okay, यहाँ पे भी तो ये equation था, तो हमने सिर्फ notation change की है, we replaced O with G. No, फर्क ये है कि ये जो equation है, चूंकि ये O outside G था, it was a point other than the center. So this equation required the axis of rotation to be non-accelerated. Now this equation does not require that. This equation is true only even if the axis is accelerating. Now, how do you see that in the diagram? You can see that here, that this point G, and remember the axis of rotation is into or out of the page, okay, crossing this G. Now this whole body, and in other words that axis can accelerate, yeah, and let's say this is the direction of acceleration AG. Yeah, you have another point P on this body for which you know the acceleration to be, let's say, along this direction. So because there are different forces in different directions, the overall effect for the center may be this way, and the overall effect for this point may be this way, the overall effect for some other point may be this way, you don't know. But what is important to know is that the axis about which you are calculating the moments, or about which you are writing the equations, the moment equations, that is accelerating, okay? So now this equation is still valid because this symmetry about G allows you to cancel any extra terms. If there are any terms here or there, they will cancel out. So this may or may not be a useful equation, because maybe you don't know details about the center of mass. So what if you have another point P, just like shown here, and you know the acceleration of that AP or AG, okay, of G or of P. So even if you know the acceleration AG, but you somehow want to write the equation of motion, the moment equations about P, not about G. So let's say you have this as a choice. आपकी मर्जी है, आप maybe problem को simplify करने के लिए you think that okay, by choosing this pivot point I may get a simpler equation. So जब आप वो लिखेंगे, so that P, because that P is not passing, that is not the center of mass, the equation will not be that simple. You will still have this term, but you will have to add another term, and that is mass times acceleration of G. Remember, you write this when you have linear equation, when you have an equation of forces, okay? But because this is moment, so you have to turn this into moment and multiply that by D. Remember, this D is the distance between this vector of acceleration and a parallel vector passing through P. The only difference between this line and this line is that this line is passing through the center and this line is passing through P, about which you want to write the equation, the moment equation. Otherwise they have the same line. So you need to add this extra term, yeah, extra term. You can think of that as the, remember आपको याद होगा हम इसको कहते थे inertial force, और अब इसको आप inertial moment कह सकते हैं, yeah, inertial moment आप इसको कह सकते हैं. But sometimes you may not be given information about AG. What if you are given information about AP? So now this equation is not then useless, okay? So then you can write the equation, the moment equation for MP in this form. You still write IG alpha, but instead of this you use AP. Now AP, because we are in a single plane, so this AP will have two components, one along the x-axis, which is APX, and one along the y-axis, which is APY. So you do similar calculation just like this, but instead of AG you use APX and APY. Now while AG could be multiplied with D, because these two are perpendicular, APX, because APX is this way, this will be perpendicular to RY. Remember, you can dissolve R into two components along x-axis, along y-axis. So just like you calculate moments, APX will be multiplied with RY because they are perpendicular, and APY will be multiplied by RX because they are these two are perpendicular, and M will not go anywhere. Now, remember this was plus because the effect here was counterclockwise. Yeah, this is counterclockwise. The reference for us is this alpha. Yeah, alpha is the angular acceleration which is counterclockwise. So this was plus because this was also counterclockwise. You can double check it. But these two, of these two, only this moment is counterclockwise. Double check it. Okay. Rx, we can write the formula R cross F. Yeah. So R in our case is Rx, and let's say Rx is towards the right, and F is M times A Py. Now Py means that you are along the y-axis. So X is here, Y is here, and if you turn this cross product, you will get this counterclockwise out of the page. So this is plus. If you apply this with Ry, and if you apply this with APX, remember Ry is this way, Px is this way. So you have to come from top from Ry to APX, and this will be clockwise, not counterclockwise. Clockwise, remember, is negative, yeah, and counterclockwise is positive. So you know how to apply these positive and negative signs. This is not different from what we have been doing in the previous lectures. So the take home from this slide is that you have the choice to use either this equation if you know that taking moments about G is relevant. If you choose any point other than the center of mass, you have a choice of using this simple equation where you just take the vector as it is, or you decompose it into two components and you write it this way. Remember, this will not change, okay? This will not change. So let's move on to the next two examples to see how this plays out. So in this example 3.41, we have a solid cylinder of mass M. Yeah, this is the solid cylinder, radius R, and it starts from the rest. Let's say यहाँ पे जहाँ से start हो रहा है ये rest position है, and because of gravity it rolls, and we assume that there is no slipping. Without means no, and no bouncing. So there is no bouncing and no slipping. That means that the acceleration will be entirely for this point, because this is the center, it will be along this direction, AGX, and AGY will be 0. AGY will be 0 because there is no bouncing. Okay, and no slipping means that you can always connect angular velocity with linear velocity. So if I put a dot there, I can say that okay, angular acceleration and linear acceleration is related to angular acceleration. Remember, this is the angular acceleration, and this A in our case, because there are only two components possible, one component is 0 because there is no bouncing, the other component must be equal to this A. Remember, ये मैं इसलिए आसानी से लेकर आऊं कि we have chosen not this to be our x-axis and this to be our y-axis because this is not useful. Because you want to calculate this one, this is the question. Question इसी के बारे में है ना, acceleration of the center of mass, AGX. So we would like our x-axis to be in line with that so that we have little computation. Or because there is no bouncing, so we take y-axis to be there. Okay, perpendicular. Having said that, you have the option of applying two approaches to this problem. Use the moment about G and then use the moment about P. So we first go with moment about G. Okay. So we just write the moment equation for about G. So if I write moment about G, I will have mg, and because the center of mass, I can simply say Ig omega dot. No, sorry, omega dot is okay. Yes, omega dot is okay. But I can simply write alpha because I know omega dot is alpha. Now I have to combine all the assumptions. No slipping. No slipping means that alpha can be replaced with, remember, omega dot here is alpha. So R times alpha is A. And that A I also know is AGX because that's the only non-zero acceleration. So I can now replace this alpha with AGX divided by R. Okay. This IG, you can look at the table that the moment of inertia of a cylinder about its center of mass is simply half mr squared. So this is from the table. And moment about G. Now, if you look at these equations, okay, remember this angle is theta between the incline and the horizontal. So this axis is along the incline, so this will be theta. And now this angle turns out to be theta. Why? A simple check is that this y-axis is a rotated version of the x-axis. So when you rotate x by 90 degree clockwise, you get y. And when you rotate this horizontal line, which is not x-axis, you don't give it a name, but you rotate this by 90 degree, you get y-axis. Yeah, no, not y-axis. Sorry. That y-axis is when you rotate this axis. But when you rotate this horizontal, you get the mg axis. Yeah. So which means that the angle between the mg line and the y line is the same as the angle between incline and this horizontal, because you rotate this to get this, you rotate this to get this. After rotation, the angle doesn't change. For example, if you have two lines with some angle, and if you rotate both of these lines by the same amount, the angle should not change. This is the property of rigid bodies. So I can now write theta here, and that means that mg cos sine theta is here and mg cosine theta is here. So I can now write the moment about G. Now, just identify which forces have their lines of action crossing G. So the line of action of N crosses G, so N will not have any moment. The line of action of mg crosses G, so it will have no moment. Yeah. The components will also have no moment because their resultant is crossing G and they also cross G. So the only force which does not cross G is this friction force. Okay. Now friction force is along this direction. This is the arm length, and if you see, because this is G, so if you think about this, you get this counterclock turning effect, and because it is in line with alpha, so that will be plus, and you will have the force is F. We don't need to write the plus sign because it's already there, and F times R. Okay, F times R. Now, so you want to write an expression for the acceleration AGX. So you might think that, okay, in this equation I do have AGX, so I can now solve this equation for AGX and bring everything down to the other side. But there is a catch. We know M, we know R, we know R squared, but we don't, and we know this R, but we don't know F. So F कहाँ से आएगा? F के लिए आपको force balance use करना पड़ेगा, because moment balance is not the only enough. We have been using only moment equation here, moment equation. और वो आपको hint भी बता रहा है कि you're using moment equation about G, but that's not enough. So we need to write force balance now. A force balance along the x-axis is सारे forces add कर दो, and they must add up to 0. Okay, force balance. तो क्या क्या फोर्सेस हैं एक्स एक्सिस की डायरेक्शन में? एम जी साइन थीटा, एम जी साइन थीटा, और एफ माइनस एफ इज जीरो। ओके, और ये बाकी तो सारे वर्टिकल में है, वर्टिकल में कोई मोशन नहीं है। So which means that f here is mg sin theta. Now I can bring that here. Now I can replace this f with mg sin theta. Mg sin theta. Now I can solve this equation because I know everything. I know theta, I know m, I know g. Actually, this m can cancel out. Yeah, and your x, I can even write the expression. Your agx will be r times g sin theta. Yeah, and this r, one of this r will cancel with this r, and this r will cancel with that r. So you will get g sin theta times 2. Okay, I'm missing something. No, I think we made a mistake. We made a serious mistake. Let me show you. It was not that simple. मैं भी सोच रहा हूँ कि इतना आसान कैसे हो गया. Basically, so we can still write f times r. That is not a problem. Equally, this basically this equation is wrong. This equation is wrong for, this equation is only valid for statics, and this is not a static problem. This is a dynamic problem. Okay, इधर आ रहा है, तो बेसिकली ये इक्वेशन हमें इस तरह लिखना चाहिए कि न्यूटन सेकंड लॉ आप लिख देना, m जिस तरह हमने ये लिखा है. So yes, this right hand side was correct, mg sin theta minus f. This is true, but this is not equal to 0. This is equal to m times agx, because हमने सेकंड लॉ लिखना है. सो यहां से जो f का एक्सप्रेशन है, अब आपके पास दो तरीके हैं. या तो यहां से f का एक्सप्रेशन लिख दे इन टर्म्स ऑफ i और इसमें प्लग कर दें, या यहां से f का एक्सप्रेशन लिख दे इन टर्म्स ऑफ agx. आप इन दोनों इक्वेशन से बेसिकली एलिमिनेट f, ये आपकी मर्जी है. आप ये वैल्यू कैलकुलेट करके उसमें प्लग करें या इससे प्लग करें, आपकी मर्जी है. बट यू विल बी एबल टू एलिमिनेट f बिकॉज इट्स ऑन बोथ साइड्स. एक वैसे बहुत आसान तरीका ये भी है कि you just divide this, cancel out this r, and here you have plus f, here you have minus f, and you add these two equations. Okay, इसको इधर ले आए, इसको इधर ले आए, नहीं सॉरी, इसको ऐसे ही रहने दें, minus f. So minus f will cancel out with this f, और बाकी आप rearrange करके you can write the equation for agx. Okay, that was part A. Now part B is about trying the same thing by writing moment equation P. अब P के around जब moment लिखते हैं तो you will have to use this equation. Remember this one, yeah this one, whichever is sensible. So हम most likely ये use करेंगे, ये वाला, क्योंकि हमें पता है कि जो APX है APX or APY is also 0 because there is no motion. ठीक है, और APY के लिए आप इक्वेशन लिख सकते हैं, and then you just write the moments about P. अब moments about P में n will have no role, this mg cosine theta will have no role, but this mg sin theta will have a role. So mg sin theta times this arm length, which is r, this is your moment, and you write, okay, ig alpha, and which is a gx over r, and then you write those two equations, one for apx and one for apy, and this is ry and this is rx, this is m, this is m. So this is an alternative, and similarly you can combine this with force balance and you can eliminate the intermediate variables. So this is just a practice for you. Ideally this B should take less time because I think you don't need to combine force balance with this. So about G you had to include force balance, if you remember. Now the difficult part is this one. Obtain the frictional condition required for the cylinder to roll without slipping. Okay, without slipping. अब विदाउट स्लिपिंग का मतलब ये है कि आपका जो फ्रिक्शन है, फ्रिक्शन का एक्सप्रेशन हमने कैलकुलेट कर लिया था पिछले पार्ट ए से और पार्ट बी से भी. सो वो एक्सप्रेशन, assuming that you know that expression, but we also know the maximum value of the friction. The maximum value of the friction we know is mu s times n. This is your n. और हमें n भी force balance से मिल सकता है. Remember, because there is no bouncing, so we can write n to be equal to mg cos theta. Okay, they must balance out each other. So I can write n to be mg cos theta. Okay, so the condition, because now you have the expression for f, you have the expression for f mx, the slippage will not occur as long as the friction is smaller than the maximum. क्योंकि जब आप ये maximum को exceed कर जाएगा तो फिर वो dynamic friction शुरू हो जाएगा. dynamic friction में फिर क्या होता है, वो फिर slippage होता है. तो इसमें कोई slippage नहीं है. ठीक है, you will simplify this and you get the detailed condition for no slippage. The last example is, it looks scary, but I think it's very simple compared to what you have been doing so far. The only difference is that it's a rear wheel drive, which means that the engine torque produced, the torque T produced by the engine is transmitted through the axle to these two rear wheels. Yeah, तो ये एक है, इसके पीछे दो हैं. So normally तो हम ये लिखते हैं कि यहाँ पे n लिखते हैं और फिर we write this n for one wheel and then you multiply it by 2 for two wheels, and similarly for this one. लेकिन इस question में he wants you to use a notation which is different, so that B is for back, or maybe you can simply call this A and B. So you define NB in such a way that half of it is on one wheel and half of it is on the other wheel, and that will give you the simplicity that NB will denote the overall force on both the wheels. Okay, so अब अगर ये NB है और ये उसका friction है, maximum friction F max. So because it's a rear wheel drive, this torque will tend to rotate this, and in so doing it will contact with the ground, and that contact will result in this reaction force from the ground, which is the friction force, and that will be, normally your force can be anything between 0 and the maximum, but here it is equal to maximum. Why? Because of this statement. Just read it out loud. When the rear wheels are on the verge of slipping, देखो ना, आप no slipping से slipping में आ रहे हैं, तो ये जो slipping की boundary है, verge of slipping, इसमें ये F maximum आ गया है. Your F now becomes F maximum, और इसके बाद ये static का maximum है, इसके बाद dynamic शुरू हो जाता है. ठीक है. So that's why this this mu s and b, we can write this because we know it's the maximum friction, and this has to be torque divided by the radius of the wheel. So that is easy. A dimensions given है, you are given this dimension, you are given this dimension, and you are given the dimension of the center of mass from the ground, which is h. ये h है. तो ये तीनों values भी given है, h, lb, la. Now what you need to do is, and mass of the vehicle is also given, you want to write the maximum acceleration. Now maximum acceleration is not a big deal, क्योंकि verge of slipping में आपको maximum acceleration ही मिलेगी. ठीक है. and that is AGX. Yeah, we again can assume that there is no vertical motion, no bouncing. When there is no bouncing, all the acceleration will be along the x-axis. So AG के लिए जब हम equation लिखेंगे, so we can simply write m times AG equals forces यहाँ पे क्या क्या हैं, horizontal force यहाँ पे x के लाइन में सिर्फ ये वाला है mu s n b which is equal to t over r according to this. Okay, there is no other force. Yeah, remember कोई applied force ये काट नहीं है कि आप उसको इस तरह पुल कर रहे हैं. इंजन टॉर्क प्रोड्यूस करता है, वो टॉर्क व्हील को घुमाता है और वो व्हील जो है ना अर्थ को के साथ इंटरेक्ट करके अर्थ उस पे जो रिएक्शन फोर्स फ्रिक्शन के फॉर्म में, ये वाला रिएक्शन, ये वाला नहीं, ये वाला. सो बेसिकली द कार मूव्स बिकॉज ऑफ दिस फ्रिक्शन. तो ये फ्रिक्शन हमने यहाँ पे मैक्सिमम फ्रिक्शन बिकॉज ऑफ द वर्ज ऑफ स्लिपिंग, तो हमने ये लगा दिया. ये सिर्फ रियर व्हील के लिए है, ये रियर व्हील के लिए. रिमेंबर फ्रंट व्हील पे चूंकि कोई ड्राइव नहीं है तो फ्रंट व्हील में ये वाली इक्वेशन जब आप फ्रंट व्हील के लिए लिखेंगे तो यहाँ पे 0 होगा. ठीक है, ये वहां पे 0 हो जाएगा. ये बेसिकली ये AGX जो है ना, yeah, okay, because it's a rigid body so we can still go with this. Now we will write the moment equation. Moment equation आपके पास चॉइस है, आप चाहें तो वो मोमेंट इक्वेशन अबाउट जी लिख दें. तो अबाउट जी आपके पास क्या क्या है, उसका फायदा ये है कि यू विल जस्ट राइट एम जी इक्वल्स आई जी अल्फा. ओके, सो एम जी हमारे पास क्या है, आप यहां से स्टार्ट कर लें. म्यू एस एन बी which of course is t over r, लेकिन वो बाद में हम प्लग कर लेंगे. This multiplies h, और if you think about this, about g इसका जो impact है वो clockwise है, तो दैट्स विल माइनस. ये लाइन को क्रॉस कर, वो g को क्रॉस कर रहा है तो इसका कोई मोमेंट नहीं होगा. nb का क्या होगा, nb multiplies lb, और इसका इम्पैक्ट काउंटर क्लॉकवाइज है तो दिस विल बी प्लस. सिमिलरली na multiplies la and this also has a clockwise effect, so this all will give you the total moment. अब अल्फा यहाँ पे क्या है, हम यहाँ पे एज्यूम कर रहे हैं कि कार सिर्फ ट्रांसलेट कर रहा है, नो बाउंसिंग एंड नो रोटेशन. इसका मतलब है कि this alpha must be 0. Yeah, so you have one equation from here, one equation from here, combine these two equations, eliminate the intermediate variables, and you get your expression. यहाँ पे remember the goal was to determine the maximum acceleration of the rear wheel drive as a function of the friction coefficient. Remember ये हमें सिर्फ इसका चाहिए था, रियर व्हील ड्राइव का सिर्फ इसका चाहिए था. ठीक है, लेकिन उसका एक्सेलरेशन और इस जी का एक्सेलरेशन शुड बी द सेम बिकॉज़ इट्स अ रिजिड बॉडी. So that was it for today. If you have any question you can ask now. Let me